Okay, so this is what we started in class today. So we're still talking about related rates. So we're kind of starting to talk about just application of derivatives and why we do derivatives and how they could be helpful to us. Okay, so one of the types of problems is what we call related rate problems. So we're going to be looking at how a rate of change of one part of an equation affects the rate of change of another part of the equation. Okay, so this is where we start seeing a lot of our word problems like in calculus. So some guidelines for solving related rate problems. If we need a picture to help us kind of figure out what's going on, we'll draw a picture. We want to make a list of all our known and unknown related rates and quantities. Okay, we're going to label each quantity that changes with time. So time is going to be our independent variable in most of these problems. We're doing things with respect to time. We're going to relate the variables in an equation. We're going to differentiate with respect to time. And then we're going to substitute and solve for what we're looking for. So with these word problems, I often recommend that you read it at least twice before trying to jump in and solve them. The first time you read, it's really just to understand the problem, to see what's going on. Second time you read is to start looking at the details. And then I even recommend that third time reading so we can start writing down what we know and what we need from the problem. Okay, so one of the notes about related rates is it is often helpful to plug in any constant values before differentiating, because when we take the derivative of a constant, it goes to 0. And we'll see a problem like that on the second example. So the first example says, a pebble is dropped into a compound causing ripples in the shape of concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet and find the rate at which the area of the disturbed water is changing. Okay, so we have this pond that we're dropping a pebble in, and it's creating a ripple effect, and we're looking to see how that change is affecting like the area of the circles as they go out and become bigger. Okay, so again, I'm going to go read it line by line. So the pebble is dropped into a compound causing ripples in the shape of concentric circles. Okay, not really much information that we need from there. The second sentence says the radius of the outer ripple is increasing. So that's an important word for us. So I'm going to highlight it just like we did in class at a constant rate of 1 foot per second. And there's our unit. Remember, we talked about that idea of per being a rate of change. It tells us what our units are. It tells us what we're comparing. Okay, and then it says when the radius is 4 feet. Okay, so that's another piece of information that we can need. Find the rate at which the area, so now we're looking for the rate of the area of the disturbed water is changing. So what we did is we just kind of read it to understand our problem. So the reading, underlining, all of that aspect is what I consider to be the understanding of the problem. Sorry, and that is terrible writing. So let's try that again. Okay, so like I said, the reading is the understand part. We just want to know what's going on in the problem and kind of wrap our heads around it. The next thing we're going to do is we're going to plan. And what I mean by plan is we're going to pull out all the information that we know, all the information that we need, and then kind of get an equation that's going to relate all those things together. Okay, so we know that the radius is increasing. Okay, so when we talk about increasing, remember we're talking about a derivative, and it's the radius that's changing with respect to time. It's increasing, so we're going to have a positive rate of change at a rate of 1 foot per second. Okay, so that's something we know. Okay, we also know that when the radius is 4 feet, so our radius in this situation, we're going to look directly when it's 4 feet. It says find the rate at which the area of the disturbed water is changing. That's something we're looking for. We're looking at how the area is changing. Okay, that's our unknown. That's what we want to find out in our problem. Okay, so we know dr dt is 1 foot per second. We know our radius is 4 feet, and we're looking for our dA dt. So we're talking about the area and the radius of a circle. So we always want to look for an equation that relates those two things together. And this is a pretty simple one because it's our a equals pi r squared. Okay, so this is the planning process of getting all the information we need, figuring out what we're trying to solve for, and then now it's really time. Our next piece is what I call the solve piece. So this is where we're going to solve. Okay. So if I want dA dt, I need to find the derivative of a, so that's where I'm going to start. So derivative a gives us dA dt equals pi is a coefficient, so I'm just going to bring it down or over. And then the derivative of r squared gives us 2r dr dt. Okay. Now I can take some time to rewrite this if I wanted to. But the whole point of this problem, once I get the derivative, is to in fact plug in. So we know what r is, we know what dr dt is, and then that's going to help us solve for dA dt. So all I'm going to do is figure out what dA dt is. So we have 2 pi, of course our radius is 4. Remember, that's from this information right here. And then of course our dr dt is in fact 1 foot. And I'm going to actually include my units in. Okay, because my units, like I said in class, can tell me a lot of different things. So that's 4 feet. And then of course 1 foot per second is our dr dt. And again, I'm getting that from the information that we wrote down at the beginning. And then after this, it's just a matter of solving. So I have 2 pi times 4 times 1, which gets us 8 pi. And then my units, I have feet times feet, which is going to give us feet squared. And then, of course, per second. So our area is changing at a rate of 8 pi feet squared per second. Now, that's kind of weird. So this is where our calculators are going to come handy. We're going to actually calculate what that 8 pi is. So 24 point something, or a little bit higher. So 8 pi in my calculator. Then I get that it's 25. And here I'm going to use my approximate symbol because now I'm rounding. So 25.1327. And we always go out 4 decimal places, and you don't have to round. If you want to round the 4th decimal place, go ahead. Okay, and then of course, feet squared per second. And that units kind of makes sense because area is in our second degree, so our units should also be squared and be in the second degree. Okay, so then I'm just going to quickly answer the question in a sentence. I need to have 3 important things, and we've talked about this before in class. I need to have the noun, the unit, and the timestamp. But not really the timestamp, but really the value and the the number, the units, and the time. Okay? We're not going to have a time in this case, though. So I would say that the area of the circle is, and I can say increasing or changing, at a rate of 25.1327 feet squared per second. Okay, so answering the question right there. Okay, so the second problem says a 13-foot ladder is leaning against the wall. Suppose that the base of the ladder slides away from the wall at a constant rate of 3 feet per second. How fast is the top of the ladder sliding down the wall when the base of the ladder is 5 foot from the wall? Okay, so there's a couple things we know. We know that we have a 13-foot ladder. Okay, that's going to be important. And then it says, suppose that the base of the ladder slides away. So the base of the ladder is sliding away at a rate of 3 feet per second. How fast is the top of the ladder sliding down when the base of the ladder is 5 feet? It's kind of hard to figure out what this is. So this is a case where I'm going to definitely draw a picture to kind of model the situation. And then this is also going to help me assign some variables because the equation might not be really evident from just looking at the picture. Okay, so I have a wall. Here's the ground. And I have a ladder leaning up against the wall. That is not a safe ladder, so don't get on my ladder. This is kind of an embarrassing ladder. Okay, And then we know that this ladder is 13 feet. Okay. So that's a really important thing. So looking at the picture, hopefully everybody sees a right triangle. So anytime I'm dealing with a right triangle, I automatically label A, B, and C. Because that's going to help me develop my equation, and then really A, B, and C, I'm hoping you guys realize that now we're starting to talk about Pythagorean theorem. Okay, so understand part, my plan part, now my pictures, and now I kind of want to pull out all the things I highlighted and kind of give them a name. Okay, so that it says, suppose the base of the ladder slides away from the wall. So B is going that way. So if we think about the length of B, B is in fact increasing, therefore that rate of change should be positive. So dB, dt, okay, and this is why I needed a variable so that I can name it for my derivative, is a positive 3 feet per second. Okay, and then it says how fast is the top of the ladder sliding down? So our A is sliding down. So our A is going to be decreasing. And that's really what we want to find, is how fast is the ladder sliding down? Well, that means we're talking about a rate of change. So we're talking about how fast it's happening. So dA dt. That's what we want to know. Okay, and then it says when the base of the ladder is 5 feet from the wall. So our base of the ladder is represented by B. So B is equal to 5 feet. Okay, so that's all the information we have. So if we think about the length of A, the length of B, and the length of C, that relationship between those three variables is going to go back to our Pythagorean theorem. Okay. So remember, we always want an equation that kind of represents the situation and relates all the variables that we're dealing with together. Okay, so now it's about my solve part. Okay, so it starts with this idea of a squared plus b squared equals c squared. Okay, we're going to take the derivative of this because we want dA dt with respect to time. So derivative a squared gives us 2a dA dt plus we get 2b dB dt equals to 2c dc dt. Okay, so we have our derivative. The next step in our process is to start plugging in. Okay, so we know that our c value is 13. We know our b value is 5. We even know that our dB dt is in fact 3. The two things that we do not know, in fact, there's 3 things we do not know in this problem. We don't know dA dt, that's what we're solving for, but we also don't know dC dt, and we don't know A. But if I go back to my actual triangle, I can use my Pythagorean theorem to solve for that A value first. And that's how we get our A value, going back to good old Pythagorean theorem. So I'm just going to use Pythagorean theorem, a squared plus 5 squared equals 13 squared. Okay, so we get a squared plus 25 equals 169. A squared equals 144. And that means A is in fact 12. And of course, this is measured in feet. Okay, so A we got using Pythagorean theorem. This is one of those Pythagorean triples again, like the 3, 4, 5. This is a 5, 12, 13. So now we can start plugging in. So we have 2, our A value we said was 12 feet. dA dt is what we're solving for, so it should be the only variable in the problem. Plus 2, our B value is 5. Our dB dt was 3 feet per second. That's going to equal 2 times our 13 feet. And then the dC dt. Well, C is in fact our ladder. So the question becomes, is the length of the ladder changing? Just think about that. The length of the ladder changing. Hope you realize that the ladder is not changing. It shouldn't change. It's sliding. It should be a fixed value. And what that means for us is that our dC dt is in fact equal to 0. Because the change, there is no change. Therefore, there is no slope. Therefore, there is no derivative. So we get a 0 there. So the idea of plugging in the constant, 13 is a constant value in our problem. If we would have plugged in the 13 first before we took the derivative at this step, we would have automatically gotten that, of course, 13 squared, and the derivative of that would have been 0. But it works out anyway. So now it's just a matter of actually calculating. So get 24 feet dA dt plus, and then 2 times 5 times 3 gives us 30. And we get feet squared per second. And then this is going to equal to 0. So now if we start solving for dA dt, we'll get that our 24 feet dA dt equals negative 30 feet squared per second. And then, of course, dividing both sides by 24 feet, we get that our dA dt is equal to negative 30 feet squared per second all over 24 feet. Which kind of makes sense because we did say at the beginning of this problem that our dA dt should in fact be negative because it is decreasing in length. So then after that, I could leave it as 30 over 24. I could even simplify it. But I want the actual decimal value. It just makes more sense when we're talking about how something is changing to kind of give the decimal value. Okay, so we get negative 1.25. And then our feet squared over our feet is going to give us back feet per second. Okay. So I would say the latter is sliding down at a rate of, and because I've already implied that we're going down, which implies a negative value, I don't want to describe my rate right here as negative. We're going to describe it as 1.25 feet per second. Okay, remember, sliding down implies that the derivative or the length is decreasing. So we don't want to do decreasing and then also give a decreasing rate. Okay, so that's kind of how we deal with that type of problem. Our last problem, sorry, didn't mean to do that. So our last problem is kind of a weird problem because it goes back to geometry and understanding what's going on in geometry. So this is a man 6 feet tall walks at a rate of 1 foot per second toward a light pole 16 feet tall. When the man is 10 feet from the base of the light, what rate is the length of the shadow changing? Okay. So we have a man that's 6 feet tall. That's going to be important. He's walking at a rate of 1 foot per second toward. Okay, so that's going to give us the sign of our rate of change in a minute. Okay, then we have the pole that is 16 feet. And then it says when a man is 10 feet from the base, okay, what rate is the length of the shadow changing? Okay, so it's kind of highlighting a lot, but we're going to stick to those words that we highlighted and kind of pull it together as a problem. This is another one of those where drawing a picture is very important. Okay, so I'm going to draw a picture. So let's pretend that this is in fact the light pole. This is the ground. Okay, if we want to put light's coming out of here. I don't know what that looks like, but whatever. Okay, remember I'm not an artist, I'm a mathematician. Okay. Then we have a man. And he is walking towards, I'm just not doing very good at my drawing here. Okay, so we have a man. He's walking towards the light bulb. It kind of looks like he's running right there. Okay, we know that the man is 6 feet. So this is 6 right here. Okay, and we know the light pole is 16. So this is 16. So the light shines on this man, and what it does is it creates a shadow right there. Okay, so the question becomes like, what equation would we use? Okay, so I'm going to assign some variables. I'm going to assign that the distance he's away from the light pole, because it does talk about in the problem, as x. So that's going to be here. And then his shadow length, which it also talks about, I'm going to label that as y. And the reason I want to put some variables on there is so that I can define what my derivatives represent. Okay, so our man is 6 feet tall. We have that on the picture. He walks at a rate of 1 foot per second towards. So he's moving this way towards the light, which means my x, which represents the length between the light pole and the man, is changing. So I'm going to use dx dt. And because he's moving towards light, that distance is in fact decreasing. So negative 1 foot per second. Okay. And then it says when the man is 10 feet from the base. So again, it's referring to that distance between him and the light pole, so x. So when x is 10 feet, what is the rate? The length of the shadow is changing. So now it's referring to that y value right there. So how is his shadow changing? So now it's talking about dy dt, which we don't know. And then the ultimate question always in these problems is, what kind of equation can I pull together that's going to relate the x, the y, and of course all the values that I have on my picture? Well, going back to geometry, when we talked about proportional triangles or similar triangles, we use proportions to solve for lengths of situations just like this. So I'm going to go back to that idea of similar triangles, and I'm just going to set up an equation that involves all the things that I have in my picture. Okay, so I know that the ratio of the height of the pole and the height of the man, so 16 to 6, should be equally proportionate to the entire base of the triangle, which I'm going to say is x plus y, to the actual length of the smaller triangle, and that's just represented by y. There's about 4 different ways I could set up the proportion that would give me the same thing. Okay, so this is kind of the equation that relates it back to the problem that we're dealing with. So the question is, take the derivative. Now, if I take the derivative as is, I'm going to have to use my quotient rule, and that kind of makes things a little bit tricky. So one of the things that we can do here is maybe simplify this equation. And the way I would do that is through cross multiplication. So we're going to multiply 6 times x plus y equals y times 16. Okay, I'm just going to simplify this really quickly. Distribute the 6, and I get this. Now, even here, I could take the derivative, figure out the answer, everything would be good. But one thing that I could also do is simply combine like terms. So I'm going to subtract the 6 out to the other side to get 10y. That's going to make my derivative a lot easier to take and a lot less to deal with. So now that I'm in a problem, I can just take the derivative now. Okay, so 6 and the derivative of x gives us dx dt, because remember we're taking derivative with respect to time, and if we weren't sure, we could always go back to our units, equals 10 dy dt. Okay, and now it's just a matter of plugging in. So 6, our dx dt gives us -1, and I'm going to even use my units really quickly. Equals 10, and then of course dy dt, which is what we're trying to solve for. So we get -6 feet per second equals 10 dy dt. And then, of course, dividing by 10, we get negative 6 over 10 feet per second equals dy dt. Okay, and then if I wanted to simplify that, we get negative 6 over 10, gives us a decimal value of negative 0.6. I don't know why I needed a calculator for that. Negative 0.6, and of course, feet per second. Okay. So I could say that the length of the shadow is decreasing at a rate of 0.6 feet per second. Okay, so go ahead and try some of these problems on your own, and then when we get back in class, we'll of course, or when I get back in class, we'll of course go over any questions you may have. Okay, if you have any questions, come and see me.